So we're going to go over problem 2 in assignment 1, and then I'll be going over 3 and 4 later. So for problem 2, we're using the Monte Carlo dropout for uncertainty estimation. And basically, the idea is that we're going to implement this Monte Carlo dropout just so we can estimate the prediction uncertainty of the neural networks. So to do that, we're going to download this data set here. And this dataset has 392 samples with 7 features, but we're just randomly going to select 342 samples. That's just for model training, and then 50 for model testing. Afterwards, we're going to use the feedback regression model with the dropout and then actually implement the Monte Carlo, just so we can estimate the prediction mean and standard deviation. And then afterwards, we're going to go ahead and do some model testing where we're getting the model, to run through a loop 10 times with the dropout so we can calculate the mean and standard deviation. And then afterwards, we're going to plot it. And so we're going to use 2 different dropouts, the 0.3 and 0.5. Okay, so let's go ahead and actually go over it. So this is the dropout rate of 0.3. On a next code block, you'll see it's for 0.5. Okay, so like I said, the goal of this problem is to estimate the uncertainty using the Monte Carlo dropout in a neural network. So first, we're going to go ahead and just load our data. Since the file was a link, I just went ahead and converted it into a text file. And then I passed the file into this method here. And that just reads the LBSVM format file, and then I could actually extract the features and targets. So this block of code right here, the idea is that first of all, I'm creating variables called x and y, and x represents the features or inputs of the data set, while the y represents like the ground truths of the data set, or you can call them output, whatever you prefer. I'm going to call them ground truths. So what I did is I had to convert the x variable to a dense numpy array, since the load, this method here, returns a sparse matrix. But later we're going to be using PyTorch tensors, and they do not support sparse text. Sparse matrix. So this is why I converted them into dense numpy arrays, and then for why I reshaped it for the PyTouch. Then later I basically did something called data splitting, and this splits the data into like a training set, which is training sets are just sets where models learn like certain patterns that it picks up when training. So the idea of it is that this is used just to pick up patterns, and then also that's just for training. Now for testing data, this is important because these sets, it shows that the data that the model has never seen before, and that evaluates its performance. So with testing sets, the model has never seen this data. So that's what we did here. So this is the data splitting. And remember, in the problem, it says we're only supposed to use like 342 samples for the training size, and then 50 for the testing, 50 for model testing. So that's what this line does. And then also we had to implement the random state to make it truly random. Okay. So after that, this whole block helps us. We're trying to convert into the PyTorch sensor, since, like I said, like this later down, we're going to use something right here called nn.linear, and that requires them to be tensors. So that's the point of this block, is to translate these PyTorch sensors, because later we're going to need them to be tensors. Okay, now we're creating here a data loader for batching processing, and that's because so we have here this variable called train_data_set, and that's a variable where we create by wrapping the tensor dataset method around the input data. So you can see that we pass in the X train tensor and the Y train tensor. And this just makes the input and ground truths into pairs. So now the train underscore loader, what that variable does is that it sets like the data loader and it takes in the train data set and then set the batch size to 32. So that means it just can process like 32 samples per iteration. So this helps with like reduce the load so we don't have to process all the 342 samples at the same time. And then we set the shuffle to true so it can be randomized. So that's great. So now this portion of the code, this is really important because now we're defining the neural network. We were asked to train, like I can go back, we were asked to train a 3-layer, multi-layer perceptron, which is just a type of neural network, neural network. And but they ask us to train a 3-layer MLP feed forward regression model with dropout. So to accomplish this, we are using the NumPy n dot module. Where it is? N part module. Did you right here? We're using this guy method. And then we're using the dropout method to reduce the potential of the overfitting of this model. So by dropping any neurons during training, this is how we're making sure that we're not making the model overfit, because that's bad and that's not what we want to do. And so this class right here, the idea of that is the neural network class that inherits from the PyTorch NN.module. And let's see, this init function here is really important because it helps initialize the 3 layers and the parameters of those neural network. And so with this, we rounded the dropout and we set the rate to be 0.3 right here, 0.3, which will be dropped in about a third of a neuron. So that way in the next round of coding, it would set to 0.5, which is the next block that I was talking about. And then we're just going to compare the results there. So in this class, we also have another function called forward, and this one is the the forward function that serves to perform like the forward pass that we were asked right here, this guy. So to do that, it just basically the aim of it is just to tell us if the data, how the data flows through the network. So that's all what this does. And it is important to note that we are also dropping neural networks even during training and testing, so we can estimate the level of uncertainty. And so that's why this is called the Monte Carlo dropout. So just this method helps with like the network to ensure the randomness by running it multiple times, and we're calculating the mean and standard deviation. Okay, and so this block of code here, we're just initializing the model, the loss function, and the optimizer. And that's important because like right here, we create the word model, which we're going to use a lot later. And that creates like the instance of our neural network. So we're ready for like training and making predictions off of this variable. And then this line right here, it just aims to define like the loss function. And basically the loss function just helps us measure the difference between like the predicted output and the actual ground truth. And that is important for like training purposes because we want to minimize the loss function. And to do that, we have to like adjust the weights of the model. And then lastly, in this line of code, the optimizer, we just basically help to update the model weights. Okay, so that's good. So now we're on to like training loops. So we're just going to be talking about essentially these two. So first of all, we're allowing the model to be trained so it can adjust its parameters so we can minimize the loss function. And so for each loop, a batch of data is passed where it computes like the loss function, but also updates the model's weight. So that's why we set the NumPy, the approach to 100, so the model can learn from that data. So that's what this is doing. And then this is the step I was telling you about, where we update the weights. And this is where we reset the previous of gradients. So that's the point of this. Okay, so this function, we use the Monte Carlo prediction T, and we set it to 10 so that way the model can run 10 times on the test data. And where this is where they drop the neurons. Here we're also calculating a couple important values. So we're calculating the mean prediction and the standard deviation. So just wanted to point out that when we're calculating the mean prediction, it's along with the standard deviation. So the aim of it is to estimate the uncertainty of this model. And then after that, we printed the mean and standard deviation. Right here, we're printing the first 5. This is just to ensure that we are converting them into NumPy and they haven't been lost. They're in NumPy format in arrays. And so now we're okay. So in the here, it asked us to sort here according to increasing order. So to do that, for later, so we don't sort out here beforehand, I just sort out in increasing order of the y, and then I've also sorted out other values here, making sure that they are increasing order. That's what this does. And then I'm sorting out these values, and then I calculate the lower bound, upper bound, and then now we're actually plotting it. And so now when we ran it, I can wait a bit and show you what it shows. So this is what it looks like. Now, that's just 0.35. I will come back and actually, you know what? I'll just go ahead and talk about it now. I was going to go through this and explain line by line again, but this is the same code as this, except we modify the dropout rate to 0.5 and not 0.3. And so I just ran it, and now this is what it looks like. So, before comparing the dropout rates, we have to kind of understand the graph a bit more. So both of this is just the red dash are the upper and lower uncertainty bound. So I can show you where we calculated that right here. This is where we calculated it. And the aim of this is to show us the range of possible predictions given the uncertainty that estimates like the Monte Carlo dropout method. And so this is how we calculated that. So if this part is like narrow, essentially as the red dashes get narrow, the narrow just simply tells us that the model is like really confident, which implies that it has lower in uncertainty, since like the standard. So to calculate it, the standard is like the standard is like really small, and so this comes out to be like a bigger number, and then same thing here. And so, but if the gap here is wide though, that makes the model less confident, and that means that we actually have higher uncertainty, and that means the standard deviation is actually really large. So yeah, now let's get into the dots. So first of all, the green dot here, you notice it stands for the ground truth. And again, ground truth is what? It's the y. And then so ground truth is the output of the model. And then the blue, let's see. The blue is the predicted mean, which is the y I had. And then let me see the predicted mean. Yes. So now if those two, if the predicted mean shows that where the model best guess is for the output using the Monte Carlo dropout. So ideally, if the blue dots are closer to the green, it basically just shows that the model's like really good at predicting the true values, right? So that's what this is it we could get information from. So now actually let's interpret what the graph is saying. So if we compare 0 0.3 to 0 0.5, you can tell that just off the bat, like looking at this bar, 0 0.3 has a large is a lot narrow than 0 0.5. Um, and so 0 0.3 had like a narrow gap for the upper and lower bound. So remember, when we say it's narrow, it has lower uncertainty, which means that the model is more confident. So now, by increasing the drop arrow to 0 0.5, that means we're dropping more neurons per iteration. So we're dropping more neurons per iteration. So if we drop about half of a neuron, which is 0 0.5, that introduces more randomness to the prediction. So if we have more randomness, that means there's more variation between the predictions, and that just leads to a higher uncertainty, which we can see based on just the gap itself. And then also, if we look at the average mean, the average mean for 0 0.3 actually comes out to be 27. Let's see. It's about, I computed it. It was like 27.51, and the average standard deviation kind of comes out to be like 6.38. But then if we compare the numbers of 0 0.5, the average mean is 24.25, and the average standard deviation is 8.66. So already with 0 0.3, graph is a lot more accurate, has less uncertainty, and is more confident. Okay, so that is it for problem 2. So now if we just jump to problem 3, I'll go ahead and run it. So by revisiting problem 3, I will explain how you could run the code, but essentially the goal of this is to train a Gaussian process regression model on a data set and predict like the target values and their uncertainty. So, and we had to use the GPR on a real data set, and this is where we get it. We'll just click on here. And with this data set, it has 3,107 samples with 6 features. And then it asks us to randomly select 150 sample just for model training and 30 for model testing. Okay, so it's kind of similar. This is pretty much similar to number 2. But now the second part of 3 asks us to train the GP regression model using the training set, and we have to test our model with that training set. And yeah, so I'll go ahead and just walk through it, the code now. So here I imported some packages. Again, I called this one, I downloaded it, translated to a text file, and then I used the same method as problem 2 to translate it into, actually this gives us information if I hover over it. So it just loads the data into an LB, a libsvm format. And yeah. And then the output of X and Y, it actually was a sparse matrix. And again, later down, we're going to need to translate that into a NumPy array. And so briefly, X just stands for the matrix, like the feature matrix, while the Y just stands for the target values of the sample. Okay. And then afterwards, we're going to standardize some features. So we're using this standard scalar method to standardize these features in the matrix. And then, so by the way, when I say standardize, I do want to mention that we make the mean 0 and the standard deviation 1. That's what I mean by standardize. So, yeah. And then once this was done, we can improve the performance and convergence for the GPR. Okay. just like what this part said. This one's similar to problem 2, where the assignment asks us to train 150. See, trains. Let's see where it says that get 150 for model training and 30 for model testing. So that's what that line does, and we made the shuffle to true to make him randomized. Set the yeah. So a part of the GPR, it has a kernel formula, and it uses the kernel formula for length. Um, so just to kind of like backtrack why we're even using this is because like the GPR uses like the kernel function, and the aim of the kernel function, it just defines like how similar two points are, and they measure the length. So here we're using RBF formula, as you can tell, um, and we pulled that formula from the slides, and I'll show you in my report. I've mentioned the formula that was used here. So essentially, we use kernel for model performance. But yeah, so now if I go back to this guy, now we're going to be talking about training. So yeah, so the kernel formula, like I mentioned, we're defining the structures for GPR. Again, that's why we're just trying to compare 2 points to see how closely related they are. Okay, so let's just jump into the training part, training GPR. We're using the fit method to train the model on our training data set. And to do that, we just grab that method and we pass in the training data set for the X and then for the Y. And then we just start making, the model will start making predictions, and we store them in Y predictions and Y standard deviations. So the Y underscore pred just represents the mean value for the sample test, but then this guy right here, he represents our predicted standard deviation and the value for each of our samples. So essentially this value just tells us the level of uncertainty for each of the testing samples. So now it's time to plot. Well, I guess before you plot, really you gotta loop, right? So that's why I looped them. So before you even do that, there's 2 features that we're looking at for j equals 1 and j equals 2, because it says we have these 2 features. We are going to loop through the features and then plot our results. So we have 2 features. The first data, we want to go ahead and first sort it out, right? Here we have it sorted out because they're all over the place, and so if we want to show it linearly from increasing to decreasing, that's what we had to do. So we sorted those features out, and then we went ahead and just plotted it. I'm just going to go ahead and just jump into explaining it because this is pretty much kind of self-explanatory. So we have 2 graphs here, feature 2 and then feature 3. So for this graph here, I wanted to highlight that this pink shaded part is our confidence interval, which is at 95%. And then the black dots here represents our training values, and then the red dots here represents the predicted values. So when we say the black dots represent true values, it could be also called ground truth values, i.e. it's the Y test. That's what that is, of the 30 samples that we had to do. And then the red dot just represents, again, predicted values, but specifically the variable Y pred, the Y underscore here. Okay. So that's what the red one is for each sample. So if the red dots are essentially close to the black dots, it just means that our model is predicting really accurately. And the pink shaded, again, is the 95% confidence. In order to calculate that, we did use a formula. to calculate that. We did like the mu of I plus or minus 1.96 of sigma I. That's how we calculate the shaded part. So again, going back, kind of similar to problem 2, where if the gap is wider, it just means higher uncertainty. And that's how we can read these graphs. So now the time tell difference between them. So let's just, I guess, go back to this graph here. You can tell most of the true values, which are the black dots, are within the interval confidence, and that means like the model uncertainty estimation is pretty actually accurate, which is great. But if, let's say, if if there was a wide gap, like right here, you see this part, yeah, that's a wide gap. It implies that the model is like not that confident. But if it was smaller, then it would have been confident. So according to this graph here, if we look at it, the predicted values, again, red dot, are close to the true values, which is the black dot, between like, let's see, they're pretty close to like around here, about 1 to really here. So from 0, 0 to 1.0. So overall, the graph has a narrow confidence when you compare to the next graph over. I'll show you. But first, like, it has pretty much of a narrow confidence around, let's say, I think actually here and here is pretty confident. But areas like almost here to negative 0.125 and down are not that confident because that's a really wide gap. So overall, the model is not that for this part is not that accurate. But if you compare in the as a whole, the model does have some areas that are predicting accurately than some regions. Now, reasons why this could have been the case where certain areas are not as confident as others is because certain areas have fewer data points, and that's why it makes it harder for the model to predict. So now if we look at feature 3, you can tell pretty much that the true values and predicted values were within the confidence gap, which is the pink, the pink shaded part. And for the most part, like, the predicted values follow closely to the true values, but you can tell that they do have a greater variance when comparing to feature 2. So, and also there's more like wider gaps in this graph to me. And this just shows to me that this graph, it's a lot less confident than compared to this graph. And so this kind of signifies if it's like not that confident, that means it has a higher uncertainty rate, and that just implies that the variance it's a lot higher. So reasons of this could potentially be because either feature 3 is just too complicated for the GPR, which this shows that maybe this isn't the best method to analyze the data with than compared to feature 2. But other than that, like, on the other hand, like, feature 3 could have like less data, which made it harder for the model to predict. So and that just means that we need more data in order to solidify any accuracy for this feature 3. So that's all with what this means. So now going on to problem 4. Now we're using the Bayesian optimization. So basically here, the goal is to use the Bayesian optimization just for a minimization problem by using the lower confidence bound as the acquisition function. So in essence here, we're just using the Bayesian optimization just to show how the surrogate model approximates the objective function by going through an iteration and just updating those new points. So jumping back, I will go ahead and run this and explain through how we get this graph here that soon is going to appear. Again, We imported the necessary packages. So pretty much for this problem, it was kind of a complete the rest of the code problem. So most of this already existed. So first of all, we went ahead and defined the objective function. And reason why we need this is because essentially we're in a situation where we have a black box function, and black box functions are functions that are just for the most part unknown to us. We don't know what it looks like, and it also has some noise. So you can see here we have noise equal to 0.1. And so the noise kind of contributes to the uncertainty. And so the aim of it is to minimize the black box function as much as we can. So next, to do that, we're going to use the surrogate model. So this function is the surrogate model where it uses the Gaussian process regressor, and we're passing in model, which is what that is the GPR essentially. And we're going to try to approximate the function. So with this whole block, this whole function, the aim of it is just to predict both the mean and the standard deviation for the input x, which is why we're passing it. And then just let you know, like the x again represents input, aka features, and the inputs will be either like a 1 or 2D array of the inputted sample. So we're going to catch here any warnings that when making a prediction, and then when we're done, we can go ahead and return it. So that's what that does. And now we're defining our acquisition function. So when we define the acquisition function, the idea is that we're trying to predict where the next sample will be. And to do that, we have to use the lower confidence bound, which we have a formula set here, which is just mu minus 1.96 times the standard deviation. So the reason why we're using the lower confidence bound is just to encourage exploration by using the predicted mean and standard deviation. And so again, standard deviation helps to indicate the level of uncertainty. So after completing that, then we optimize the acquisition function. And when we do that, we're trying to optimize it so we can find like the next best point. So for this function, we just pass in the input sample, the target value, and the model. So again, when we say like the model, in this case, it's just the GPR. And so here were the ideas that we're generating 100 random samples between the domain of 0 and 1. And this function is just going to return the minimize acquisition score. So now we're going to go ahead and start defining the process regressor and fitting the model. So I just want to show you. So here we're just basically defining the surrogate model, which is again the GPR, and we're going to use the maternal kernel. And that basically aims just to help us to define the similarities between the two data points. And we do that by correlating the points like based on their length between them. And it's like right here. This is where we're doing it, by the way. This plot is just going to get called later. So we're just going to skip it for now. So we're just going to go here. And this is what we're talking about. We've already generated the randomness. We already set it as array to double check. We're just reshaping it. But here's where we define our model, which is the GPR. And it's going to be using the maternal one, which is the length. Okay. And then after that, the alpha right here represents like the noise level in the data. And then this guy here just represents, it just allows us to like restart it multiple times in order to find like the best kernel parameters. And then this line here is that we're using the fit model method, and we are teaching the model to use like a known sample, which is X, and then their values respectively, and thereby the model can make predictions where the next point will be. So that's what the aim of this guide does. And then now we're calling our method plot, which we pass an XY model. And then that's what it calls this. But before we get to that, I do want to explain this portion here, because once we do the optimization process, then we will plot it again to see the final surrogate function. This is really just aimed to show it what it looks like now before the optimization. And I can show you what it looks like now based on this image and versus this image. You can tell. And I will explain that later when we're done with it. Okay, so great. We went ahead and defined the Gaussian process regressor and fitting the model. And then we just plot it. And then now here we're doing the optimization process. And then we're going to plot it again. And then I'll tell you the best results for X and Y, which I can just tell you now quickly. Right here, it's 0.518, and then Y is negative 0.265, and we'll revisit that part. But anyway, for the optimization process, we're doing it by looping. And so the goal of this loop is just to perform the optimization by using the acquisition just to find the next data point. After that, we're going to evaluate the function at that point, and then we're going to update it and refit it itself into the model. And then finally, we're just going to go ahead and print it, the approximation and its true value. So that's what this optimization process aims to do. And then we just go ahead and plot it. And so now if we just kind of compare briefly, this is what it looks like after the optimization. You can see the initial. You can see that we've minimized it. As you can tell, see we overlined it. The blue is the before, and then the orange is what we did to minimize it. So just overall, just to understand what this graph is saying, is that we have orange dots and they're scatter points. You see that? They're just scattering over, and they represent the observed data. So 200 random samples were evaluated using the objective function with the noise, and the X is the input value and the Y was the noise output from that objective function. So the orange line, it represents the true objective function without the noise. So in essence, basically we wanted it to represent the actual objective function that we're trying to minimize. But the blue line represents the GPR, and let's just show here. The GP's models. So basically, when using the Bayesian optimization, we're trying to get the model to explore areas. So the blue line gets more accurate as more samples are added using that Bayesian optimization. And so we try to minimize the blue line, which is like the surrogate function, using the sample data points you see in orange. You see how there's a lot more in this area where there's differences between the orange and blue, and that's because we have more data points and we can actually minimize the function there. And when we minimize the blue lines, we use the sample data points just to refine the model, and we had to do several iterations. So based on this, our global minimum for the global minimum is around, you can kind of tell it's around 0.6, and then the best value is 0.713, and the Y value is negative 0.238, like we mentioned. I want to look for, let's see. Here we go. As I've mentioned. So yeah, that was when you're using the Bayesian optimization with the GPRs. That we're the aim of it is just to use it. So using the Bayesian optimization just so we can minimize that problem, and we had to do it to use the lower bound confidence as the acquisition function. So in the end, we used a surrogate model to approximate the objective function, and we eventually went through an iteration with using a loop, and then we updated the new points.